If you took high school trigonometry, you are probably familiar with this wave, memorizing formulas for sine of theta and opposite over hypotenuse. Textbooks strictly tie this line to right triangles and unit circles, leaving students to memorize abstract examples without understanding the underlying idea. But look closely at it. A continuous rolling wave doesn't look like a sharp triangle. It doesn't look like a closed circle. We are taught to look at the byproducts of sine rather than the wave itself. Trying to understand a sine wave by starting with a circle is a backwards premise. It is like trying to explain the concept of a straight line by pointing at a rectangular brick. To see the actual geometry of this wave, we must forget the circle, erase the triangles, and strip reality down to a single one-dimensional line. Imagine a single point of light moving back and forth along that perfectly straight vertical path. If that point moves at a constant linear speed, it looks robotic. It hits the outer edges and instantly reverses direction. But natural motion involves a more graceful, smooth deceleration. This perfectly smooth acceleration and deceleration along a straight line, the way a real spring bounces, is what we are actually measuring. That is sine. This happens because of a restoring force. At every instant, the point experiences an internal pull that acts exactly opposite to its current position. As the point travels further from the center, that internal pull gets stronger. It forces the point to slow down as it reaches the edges, and then snaps it back, speeding it up until it rushes past the middle to start the cycle again. Sine is the geometric footprint of this natural resistance and return. It is the baseline for all smooth vibration in the universe. Now let's add a second sway, a horizontal one, moving with that same smooth acceleration but offset in its timing. When we combine these two intersecting 1D motions, their mathematical intersection traces the perimeter of a circle. To measure this over time, we use a graph where the horizontal axis represents time and the vertical axis tracks the point's changing height. And we measure the distance along this path in radians. A radian isn't just an observer's angle, it is the actual physical distance the point has moved along the curve. As the dot travels its radian distance, we project its height onto our timeline. This is how the static circle unfolds into that famous wavy line. We are simply tracking percentages. It starts at neutral, peaks at 100% of its height, falls to negative 100%, and returns to the center. The circle doesn't create the sine wave. Intersecting sine sways create the circle, and the wave is simply that 1D motion unrolled across time. Because this smooth geometric footprint governs how matter oscillates, it dictates the structural integrity of the physical world. Civil engineers rely on the physics of the restoring force to manage how skyscrapers sway. By calculating the exact patterns of acceleration and resistance required to bring a tower back to its center, they ensure these structures can absorb the energy of high winds. This same geometry models the harmonic vibration and tension holding up massive transit infrastructure, predicting how cables will flex and return to center under the weight of traffic. Historically, navigating the globe relied on calculating these exact cyclical distances. Sailors used maritime sextants to measure the physical arcs of stars as they moved across the sky. Today, GPS networks rely on these same spatial calculations to trace orbital arcs. The telemetry dishes that track satellites are essentially modern versions of the sextant, solving for the same geometry of return. It also governs the architecture of sound. Every frequency handled on an audio engineering console is a measurement of air molecules swaying back and forth in a one-dimensional line. Every smooth motion in nature is eventually pulled back toward an equilibrium. From a bridge cable to a satellite's telemetry, sine remains the baseline for every object that must find its way back to center.